Hi, welcome to Imperium Learning. This video is the third video in a video series that shows you how to use your vector error correction model to do some ordinary least squares regression. We're on the final part of that video now. I'm just going to be showing you how to conduct your residual, your stability, and your coefficient tests for your least squares model. Now bear in mind, I've already shown you how to conduct the wall test in the previous video, and also how to interpret those, looking for p-values that are more than 0.05. And again, this slide just talks about how we interpret this test. So as you can see, we used our p-value, we used our wall test, which had a p-value of like 0.3 to show that these lagged values show that they are insignificant in the short run in explaining house price changes. That being said, the variables are still significant in the long run due to the presence of the error correction term. So now we're moving on to our residual tests. We're going to be using three, at least we're actually going to be using four. We're going to use the Broish-Godfrey for serial correlation. We're going to use normality. We're going to use the Jark-Berer test for normality. We're going to use the White test and the Arch test. The Arch test is probably a bit unnecessary. The White test is the most important for heteroscedasticity, but you know, it's still a good test to do. So yeah, before I apply it, here's a slide just introducing you to what it's for, the format of the test, what the null hypothesis is, what the alternative hypothesis is, and we need to be looking for a p-value that's above 0. We want it to be above 0.05 so that our model doesn't suffer from serial correlation. So let's just go back to here. This is the window for our least squares regression right here, and we're just going to go to the residual diagnostics, and then what we're going to do is we're going to click on the serial correlation, and I think we're just going to include just two. And as you can see, now bear in mind, now look at this, look at how the two conflict, because what we have here are this column here is actually the test statistic for the Broish-Godfrey serial correlation test. You can see that all it's done is it calculates the number of observations and multiplies that by the r-squared value, which is there, and as you can see, it's actually below 0.05, and yet the F statistic value shows that it's above 0.05. So I personally was unsure about how to deal with this. I think I concluded that it did suffer from heteroscedasticity, but the fact that the F statistic had a p-value of above 0.05 perhaps made it more palatable as a model. And so after that, as you can, if you remember, this was the Jark-Berer test. This is to detect whether our residuals are normally distributed. The null hypothesis is that the residuals are normally distributed. The alternative is that the residuals are not normally distributed. So if the p-value is 0.05 or less, then that means that our residuals are not normally distributed. So let's go back to Eviews. Let's do the normality test. And as you can see here, this is my p-value right here. This is the Jark-Berer statistic, and this is the p-value that's associated with it. It's well above 0.05, and as you can see, it's roughly a kind of normal distribution, and so because of that, we can conclude that the that the residuals are normally distributed, and so that's certainly a good thing for our model. So moving on, and again just moving on to the white test. This is a useful test for detecting heteroscedasticity. What's the null? The null is that the residuals do not suffer from heteroscedasticity. So basically we're hoping that we get a p-value of above 0.05 just to make sure that that our residuals are homoscedastic. So let's click on View, click on Residual Diagnostics, click on Heteroscedasticity Tests, select white. I think we can include both. We can just see what both are. First, let's start without the cross terms and see how that results. Now again, this is important for our heteroscedasticity. This is the row that we're looking at, obs times by r squared. This is our test statistic right there, 17.10945, and this is our p-value right there. And luckily it's above 0.05 with a p-value of 0.19, so we can safely conclude. We can actually do it with both. We can actually do both forms of the heteroscedasticity test here. We can include cross terms too. Let's see how that... Oh, I've got an insufficient number of observations. So unfortunately we can't do that, but we can do it without the cross terms, and we found that it didn't suffer from heteroscedasticity. Let's move back then. And now we can do some stability tests. So we're going to use the Cusum test, and we're going to use the Cusum of squares test. So just a little summary of what it does. This test is based on the cumulative sum of the recursive residuals. It ensures that the parameters of a linear model are stable over time, and it should be noted that this test is only applicable to ordinary least squares regression. So all we have to do is go back to Eviews, we click on View, we go on Stability Diagnostics, and then what we're going to do is we're going to go to Recursive Estimates. We're going to select the Cusum test, and we're going to click OK. And as you can see, the parameters are always well within the boundaries. You don't want your blue line to fall outside of these two red dashed lines. So long as they stay inside the red dashed line, then that's good. And so what can we conclude from this little Cusum test? We can conclude that our model is dynamically stable over time. And then the Cusum of squares test, it's just applied to check that the variance of your residuals are stable over time, and this is just a further substantiation of your Cusum test results. So let's go back to Eviews. How do you apply the test? You click on View, you click Stability Diagnostics, you click Recursive Estimates, you select the Cusum of squares test, and you click OK. And as you can see, the blue line is still just about inside. So as a result, I can conclude that my model again is dynamically stable over time. And so that's a good way of assessing your OLS model. Overall, it's quite good. It would have been better if it had no serial correlation, but it is what it is. And yeah, so this was the third video in a video series about using a vector error correction model to do a least squares regression. If you think this was good content, don't hesitate to subscribe, don't hesitate to give a thumbs up. Makes my videos more visible on YouTube. It might help out some other struggling students out there. So yeah, that's the end of it now. This wraps up the second video series in total. And yeah, okay, bye now.